We're going to finish chapter 7 today on atomic structure and what that has to do with the periodic table. And I'm sure I've said it before, but I'll say it again. If you know how the periodic table is structured, you can infer from it the electronic structure of the atoms, of each of the elements. I think we just left off last time with the video on the photoelectric effect. So I want to pick up with that. Did I not? Was I already down there? Oh, I know what I did. I already backed up. Yeah, this is sort of backing up. So let's do a quick, what does the photoelectric effect have to do with the quantum nature of light? The photoelectric effect is, in short, the ejection of electron from the surface of a substance, usually a metal, based upon the energy of the light that impinges. If the light does not meet a minimum of energy, then there will be no electrons ejected. And that's based upon the wavelength of the light, the color, if you will. And that's also based upon Planck's equation. The energy of the photon now, we're quantizing light into packets, the photon. So this constant value times the frequency will give you the energy of that photon. And that's a minimum amount of energy that can be calculated for the ejection of one electron. Now, the intensity of light is just more photons, but the energy of each photon does not change until the frequency changes, or by inference, the wavelength. Okay, so what does that mean about the quantum nature of light? Just what I said. It's a one photon of sufficient energy, one electron. Now, if there's any leftover energy, this is the minimum amount of energy. If there's any left over, then that energy is translated into kinetic energy of the photon. So once it's ejected, then the minimum energy is met. It just goes, it sits there. It's free from the atom, but it has no kinetic energy. But if you add a little extra, then you start getting that electron moving. Okay. These are observations that are on the previous part 1. And let's see, we did these conclusions too, didn't we? Those photons that don't have enough energy to eject an electron are called thermal photons, simply because the energy that they bring to the surface of the substance can't be destroyed. It's got to go somewhere. So it's usually converted into heat. We call it thermal photon. Okay. Is this where I'm supposed to pick up? No, those are conclusions. Once more the same. I've already described that. Okay. Okay. Did I cover this part yet?
Read the next one after.
Yeah, actually, we go down one more. Okay. I probably should just skip over this because we're going to run out of time as it is. Okay, so we're looking at this. Is that right? Okay. The controversy over the nature of light, but whether or not it's a wave or a particle, is derived from the behavior of light. Sometimes it acts like a wave, and sometimes it acts like a particle. And the evidence for wave is, one of the evidences for wave is diffraction. And diffraction is just characteristic of a wave when it meets an obstacle. It could just be an edge, as a matter of fact. It could just be an edge of some obstacle. This is first. Try a different color. That's fine. Right. If your wave meets an obstacle, the point of contact serves as another point of origination for the wave. So from that point, it starts to spread out like that. Of course, it's easier to discern if that point of contact is a slit, right, a small space. Then it moves from that space out. Okay, that's the way waves behave. How do we know that light is a wave and not a particle when it encounters this slit? If the light wave were a particle, then you would have beams of particles, right, strike the surface, and only the ones here would go straight through. And you would have a shadow over here, shadow there, and only a bright spot right there for the light. But that's not the way it happens. It's graded out. It's a bright spot here, and it gets less and less illumination out this way. So that's characteristic of a wave, diffraction. Okay. Another characteristic is refraction, which is the bending of light that's passing through a medium. We use that when we grind lenses. A lens relies upon that characteristic of waves of light. So when if a light beam hit this surface and it were particles only, it might be slowed down, but it still go in the same direction. It just go like that if it were particles. But as a wave, the wave strikes that surface. This, that, that. Where it contacts that surface there, now when it strikes this medium and it interacts with the medium, it slows down. It's kind of like, you ever seen that old movie, Ben-Hur, with the chariot race? Never seen that? Gotta watch it. You know how chariot races are, have like 4 horses and then this little buggy back here with a guy, and he's, you ever seen those? Okay. Okay, there goes my analogy. But what you try to do as a charioteer is you put your most stable horse on the inside. You've always got a turn. Track and field. In this country, it's counterclockwise. So if you have 4 people say they're holding hands and you're going around a curve, right? The one on the inside has to move slower, right? Otherwise, it'll send your whole line out into the field. But if the inner one is very stable and holds their position and moves slower, then the rest of them can move on around the curve. That's the point. So as this slows down, the wave has to change direction. So eventually, as more and more of the wave encounters that, it changes direction. So the direction was here, this is before it hit, and then it's this direction afterwards. That's refraction. The bending of the light is characteristic of a wave. Okay, you see that in prisms, see it in lenses where they focus the light or they spread it apart. Well, focus is either way. Focus to a point would be a convex lens, and the concave lens would spread it out. Depends on the type of defect in your eye as to whether you need one or the other. Now, if light acts like a particle, photoelectric effect that we've already described is an example of particulate behavior. So, Einstein said it's both, and he proved it in his 1905 paper, which eventually got him the Nobel Prize in 1921, for his description of the photoelectric effect. Okay, so let's talk about spectra. There are basically two types of spectra. What do we mean by that? It's a spread of colors. Right? For the eye, a continuous spectrum, you would see every color in the rainbow, as they say: red, orange, yellow, green, blue, indigo, violet. But when you mix them all together, what do you get? Light. You get white light. That's a continuous spectrum. Except when you shine that spectrum through a prism, like say it's coming from the sun, and the light enters that prism and it's bent by refraction. Only each wavelength bends at a different angle. Each wavelength of light, each color, does not interact with this prism in the same way. So the shorter wavelengths bend more, and the longer wavelengths bend less. So you get this continuous spectrum here. It's like a rainbow. It just grades from one color into the other. That's a continuous spectrum. And you see that from the sun, more or less. And you also see it from various light sources. If you take something and heat it up really hot, then like an incandescent light bulb, you'll get a continuous spectrum. That's not what we observe from individual elements. From individual elements, and we're going to use hydrogen as our example because it's only got one electron, and that's where it is. It's the simplest one. So it produces a line spectrum that's very simple. Right? The more electrons you get in there, the more complex the line spectrum is. But hydrogen, when it's excited, emits light in 4 distinct wavelengths, lines of a spectrum. So if you pass that light from a discharge tube with hydrogen gas in it, then you will get, pass it through a prism, you get 4 lines, and only those 4 lines. Right. So there's your, this video is not going to show because it's flash based. Right? It's not supported anymore. But the picture is valuable. There's a continuous spectrum, right, from this incandescent source. Okay. All right, so when you get this discharge tube that's filled with hydrogen and it shines light through here, it's going to produce nothing. I thought it was going to animate for me. The light would pass through here and produce 4 individual lines. Okay. Now, why is that? There has to be a reason that you don't get a continuous spectrum with hydrogen. It's a clue. It's a clue to the structure of the atom. In fact, to the electronic structure. What we're seeing is that each individual wavelength indicates energy, right? We know that from this equation, right? Or we can modify it. Let's see, wait a minute. Yeah. There we go. Right, speed of light divided by wavelength is frequency. So if each wavelength represents a specific energy for the photon, then that means that something happening in that space around the atom that only allows for this particular wavelength. And what we need is a model, something that explains what's happening. And what we get is Bohr's atom. Niels Bohr. He was a Danish physicist. He said, this is what's happening. He said, there's your nucleus, and the electrons can only occupy energy levels, these different energy levels. He gave a number, 1, 2, 3. It's very original. So the lowest one is the lowest energy because everything's relative to the nucleus. So the lowest energy is down here. And that's where this electron will be around the hydrogen atom because there's simple, that's just natural. It's going to be at the lowest possible energy state. That's what matter tries to do. But if we send in light of just the right energy, it will promote that electron to another level. If it's a certain amount of energy, it'll go up to this level. If it's a little more, but exactly the right amount, it'll go up there, or it'll go up there. We can add just the right amount to get it to these different levels, but nothing in between. That means it's quantized. Just like we found with the photoelectric effect. Light energy and movement of electrons around the atom are quantized. They can only move certain places. It's not continuous. Okay, so if you add energy and you can get the electron to pump up to a higher level, then what happens if it is already out here and it moves down to the next level? Say if it's out here and it goes all the way down here. It emits light of the characteristic energy that would have occurred had been required to promote it to this level. So this way, it emits light, and this way it absorbs light to make the transition. Okay? And if you know what the energy level values are for each of these levels, you can calculate the amount of energy required between those two levels and translate that into what wavelength of light. And that's exactly what has happened with this model. This Bohrs model can predict for the hydrogen atom, can predict those 4 wavelengths. Okay? So I just told you what. Why is it significant? You know, because those individual colors represent energy transitions of electrons. Right? If those energies were not quantized, then you'd see every color in the rainbow. And actually, that would be a bad situation. Because what we know about the universe comes to us as light. And if it's just a big jumble, there's really no information there. Helium, for instance, the next atom with 2 protons, was discovered in the atmosphere of the sun before we found it on Earth. And it was found by this procedure. The spectrum of some unknown was located in the atmosphere of the sun and identified as some unknown element. It hadn't been discovered yet. That was an empty spot. And then we found it on Earth. Where do we find it on Earth? It's not very common in the atmosphere, right? Because helium is a very light element. So it tends to float, drifts to the top, and it's gone. It just strips off that outer atmosphere. So we need a concentrated source. The most concentrated and economically available source is natural gas. We get natural gas around. We purify it. Let's see. And part of the purification process will remove moisture. Right? And we also recover helium from natural gas. And when gas production was ramping up shortly before World War I, the U.S. government considered it a strategic element because it was being used in dirigibles and balloons for military purposes. So we took it, and we took these old abandoned salt mines, salt domes under the earth. You just pump hot water into them, dissolve the salt, bring it out, and then evaporate the water, and you got salt. They're all scattered all over Louisiana, Arkansas, Texas, Oklahoma. And the government would take this helium that was purified and just pump it underground and put a cap on it. And just that's their storage, strategic storage of helium. It's still there. We still store it that way. Anyway, I digress, of course. The helium was discovered by this method. Okay, so now to the Bohr model of the atom. These energy levels, and this, by the way, this lowest energy level is called the ground state. Let's see, I better mark these attendees, Elijah and Brandy. Here she is. Okay, that's called the ground state. That is the lowest possible energy state. Now, for the hydrogen atom, it's only one electron, and it's in that first energy level. But for those atoms that have more than one proton, consequently more than one electron, the ground state might have the outermost electron may be further from the nucleus because these positions are occupied. And we're going to get to that, show you how many you can have at each level. And that's the ground state for a different element. Right? We fill up these levels, and then the ground state will be the highest possible level for that outermost electron. But for hydrogen, that N equals 1, that's the ground state for hydrogen. It's the lowest possible energy. And this is what it would look like on a diagram. So this energy level 1 here is not at the nucleus. It's some position away from the nucleus, but it's at the lowest possible energy. And then the jump from 1 to 2 is pretty big. First energy level to the second energy level is pretty big. But then as you move out, the jumps between energy levels become narrower and narrower. Okay? So what we see is, at least for these three emissions, this red, green, and blue, there's another one from level 6 down to 2 that's not shown there. Those are the 4 visible wavelengths that you can see from hydrogen. Now, there are other transitions, right, that we can't see, but they can be measured with instruments, like in the ultraviolet range or in the infrared range. They have series names, right? The people that study them and characterize them, they get their name slapped on it, like the Paschen series, and the Bohrs series, and so forth. Anyway, if we transition from one of these down to here, that's a lot more energy than can be contained in a visible photon. So we can't see it. It's higher energy, probably ultraviolet. Okay, this is another way of representing it. But in this one, the spacing looks like it's equivalent from one to the next, which isn't true. This is the level 1. They're not even showing the nucleus. So that's N equals 1, 2, 3, 4, and 5. And it just shows the transitions, and you'll be able to pick those up in a spectrum of the emission of hydrogen. Now, one other thing, remember I said that if light comes in and promotes the electron, that light is absorbed. Right? So you can get the reverse of this. If you have if you have a cool gas, so to speak, a cool gas of hydrogen atoms, not the hydrogen molecule, hydrogen atoms. So cool is relative. You have to heat it up a little bit to get them to dissociate. But then you shine light through it, say white light. White light, and it's a mix, right? Mix of wavelengths, all of them. And as it passes through this hydrogen cloud, you will get dark lines, a dark line spectrum, where this is absorbed at exactly those same wavelengths. Okay? That's how we detect elements in the atmospheres of other stars and planets, especially stars, because you have this bright background radiation shining through their atmosphere, and it produces a dark line spectrum. And you can tell from that what elements are in the atmosphere of that star. Okay. All right. So this is Bohr's formula for calculating the energy of transition. First of all, you need to know what's the energy of each of the levels, right? So here's his N number, 1, 2, 3, 4. This Z is the number of protons. So for the hydrogen atom, N equals 1. So you just stick a 1 in there. 1 divided by that N squared, 1 squared, 2 squared, 3 squared, 4 squared, whatever it happens to be, times this constant. And that's the energy at that level. Okay? And notice it's negative. That's another characteristic where you have the nucleus here with your protons, and then you have energy levels. The more negative, the closer it is to the nucleus. If you add energy to it, then it makes it more positive as you move out. When you form an ion, when you have this electron now free, it's at infinity, so to speak, the distance. So when it's at infinity, its energy relative to the nucleus is 0. You've used up all that energy. So let's see, N equals infinity, right? Which means what? 1 divided by infinity is what? Remember your math class? 1 divided by infinity is 0. So it can't have any energy at that level, not relative to the nucleus. Okay. The most stable position is right in here somewhere at the lowest possible ground state. Okay, in case you were wondering why that negative was there. That's why it's there. The more negative, the closer it is to the nucleus. Okay, so how do we figure the energy of transition? Well, it's like any delta E. It's like any delta calculation. It's the energy final minus the energy initial. Final minus the initial is delta. So if the final energy is some value and the electron moves closer to the nucleus, then this value is going to be more negative than that value. And that will give you, let's see, negative, this is negative, so that would be a positive one. And that's subtracted from this one makes it less negative. So that difference of energy is translated into a wavelength. Okay. Bohr's model only works for hydrogen. That's one of the big problems. It's a start, but it only works for hydrogen or hydrogen-like ions. That's why this value Z is there, right? So if you have, let's say, lithium, which has 3 protons, you would put a 3 there, but it only works if lithium has one electron. So you've got to, some way, get rid of all but one of the electrons. Then you can treat lithium with this model. Okay? All right. Let's see. So here's the before and after. Right? This is the level for the final. This is level for the initial. And it just depends on which way you're going as to if you're transitioning from, say, level 5 to level 2, then you know you're going from a higher energy to a lower energy. And this is a condition that would lead to emission of light. But if you're calculating from 2 to 5 energy level, this would be absorption of light. Because you're going from a lower energy level to a higher energy level, it has to absorb energy to get there. Okay? Qualitatively speaking. All right, so we can condense this formula into something a little more manageable, right? We factor out the negative sign and the constant, and then we're left with this factor here. And if it's a hydrogen atom, I mean a bona fide hydrogen, not a hydrogen light, but a hydrogen atom, then this was be the formula to use, where you just stick a 1 right there instead of anything else. Any number of protons. Okay. So for this transition from 5 to 2, let's see, 5 to 2 means it's going to emit light. It's going from high to low. And we have measured that value to be this, 434 nanometers. So if we use Bohrs formula, we find out that the energy should be 4.57 times 10 to the minus 19 joules for that photon with this wavelength. Okay. What if we calculate the energy using Planck's equation? Brain farts. Planck's equation tells us that if we plug the equivalent in meters of this, remember nanometers, how do you convert that to meters? Right? Nano means 10 to the minus 9. So it's just 434 times 10 to the minus 9. And then if you reduce that to scientific notation, you get 4.34 times 10 to the minus 7 meters. Has to be in meters. And this value is the speed of light, meters per second. And there's your Planck's constant. Then we calculate the energy of that wavelength at 4.577 times 10 to the minus 19 joules. That's how much energy is in that photon. And this is the amount of energy that was absorbed, was emitted. 4.57 times 10 minus. So within experimental error, they're very close. That's just a demonstration that it works. Bohr's model works, at least for the hydrogen atom in that wavelength. And you can do that for any of the other wavelengths. Okay. So Bohr's model works for the hydrogen atom, and it treats electrons as if they're like, it's sort of a planetary model. You know, the electrons, treats the electrons as particles moving around in that orbit. Only it's unlike planetary model, the electron has to move. It has to be in this distance from the nucleus, and it can't be in between. Of course, we know that planets can be anywhere. but it treats the electron as a particle. Let's see. So how is Bohr's model wrong? It assumes that electrons move in circular orbits, but that can't be, right? We know that when you produce acceleration, you have to expend energy, and a change in direction is acceleration. So if the electrons are moving around the nucleus, like this, like there's the nucleus, then it's going a certain velocity in that direction. But over here, it's going velocity in that direction. It has changed direction, which means it's accelerating. And in order to accelerate, you have to apply a force to that mass. That's Newton's second law. You have to apply that force to this mass. And if you don't have a force to apply to it, then the force has to bleed from the energy that's available. So if you're going to move in that direction, and let's see, let's do vectors here. So what has it done? It's gone here to here. So it's accelerated toward the nucleus that much. If that's the case, then these electrons should gradually lose their energy, and they should crash into the nucleus. They don't do that. So Bohr's planetary model is defective in that respect also. We have to replace that model with something better later. For now, it serves a purpose. Right? You can calculate the transition here and correlate it with each one of these wavelengths that are observed based upon their Planck's energy and Bohr's transition energy that we can calculate with that formula. And just a reminder, those formulas are all in useful information. You just need to know where they are in the table and know how to use them. I don't have you memorize them. Okay. So in this respect, the lowest energy, Planck's constant, Planck's equation tells us that the lowest energy is the shortest frequency or the longest wavelength. Know that red is less energy than blue. This also shows us that red energy for that light beam, it's derived from the closest jump, the narrowest jump, right? From 3 to 2. From 6 to 2, you get more energy. Less energy here, less energy there, least energy here. Longest wavelength, least energy. All right, now why do I stick Heisenberg in here? Heisenberg follows on the tails, so to speak, of Bohr's model, because Bohr's model says electrons are particles. And we assume that if you know something is a solid particle, you can tell things about it like where is it, how fast is it moving, what's its mass. Right? Heisenberg says when you get down this small, knowing where it is, that's delta X, knowing its location, and its velocity, right? This is momentum actually, mass times velocity. But the electron is constant mass. When you're talking about other changes, then the mass is irrelevant. Well, not irrelevant, it doesn't change. So we're really talking about change in velocity. So you can tell how fast it is, but you can't tell where it is. Or if you can tell where it is, you don't know how fast it's moving. And it's based upon this formula, right? If this value is greater than Planck's constant divided by 4 pi, then it depends on which value is contributing the most to that product. If you have a very large mass like you or I, then it's no problem to have a small deviation in position. So you can tell where I am because I'm such a big mass. But if I'm a very small mass, then you can't tell where I am. The delta X, or the uncertainty in location, is massive. Right? If this value is very small, then this one is huge. So you can't tell where I am if I'm an electron. Okay, so what does that mean actually? It means that we need another way to describe the electron. And which is more important, knowing where the electron is or what its energy is? And it turns out that it's more important that we know the energy of the electron rather than the position. We're going to treat the position of the electron as a probability, right? There's like a 90% chance of finding it in this space. That's all we care about. It's more important to know the energy. And the energy is roughly correlated with its distance from the nucleus. So we get some information out of energy as well about its position. Okay, so now we're dipping our toes into the probability pool, which means it's like I had a cell physiology professor who used to say, there's a very, 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 very slight probability that all the air in this room will migrate to that corner and will suffocate. Okay. We know in our lifetime it's probably never going to happen, but that's the nature of probability. It doesn't say that something will happen. It says maybe. And this is one time out of 100 million billion, it'll happen. That's all he was saying. Just to impress upon us that probability is not deterministic. Right? Up to this point, science was deterministic. Classical physics is, yeah, we know exactly what's happening. We know when it's happening. We know how much. We know the numbers we can put to it. And that was good enough for a while. But then this stuff started popping up. Physicists for a little while were kind of, they're just sitting back and enjoying the fruits of their labor. They said, we know everything there is to know. And then photoelectric effect cropped up, structure of the atom cropped up, and now they got to get off their dust and figure that one out. Or retire and let somebody younger come along and make us the reputation, which is usually what happens. Okay, so the position of the electron is a probability distribution. And in the formula for that, let's see, I clicked past it. These functions were developed by Erwin Schrödinger. Wave functions that are applicable to the electron. So now we're going to treat the electron as a wave. So if you look at an atom where you have the nucleus here, and then the electron is at this energy level, think of it as, has to be exactly, no half waves. It's got to be perfect wave around there, continuous wave. If you have half waves, it won't fit. If you have fractional waves, it won't fit. That's one of the conditions of Schrödinger's equations. Right? If it's going to be in this position, the wave that you write for this in mathematical terms has to fit that location and that energy level. So Schrödinger came up with all these wave functions, and one of the more important parameters in his waves is this psi. That's the Greek letter psi. It looks like a pitchfork. Right? If you go to most large university campuses and drive down sorority fraternity road, you can see all the Greek letters plastered on the buildings. At least one of them is going to have a psi. But this term, if we square it, it simply indicates the probability of finding an electron in that point of space. Okay. So it could be 0.75, or it could be 0.9, it could be 0.99. The higher the value, for it not equal to 1, because 1 means certainty, but approaching 1 means that you're more confident of finding an electron in that region. Okay. The only place that we have no confidence of finding an electron in a region is where the probability of the chi-squared is 0. And at those points, we call those nodes. There's no probability of finding an electron there. Okay. So what does that look like in reality? Well, representations can help us. This is three-dimensional space, and it's a mathematical description. So we can't go in and take a picture of it. We can have artists draw, or computer programs draw what we think would be the distribution. And this is only a two-dimensional map. It's like a cross-section of a 1s orbital. Now, what's a 1s orbital? Well, we haven't got there yet. But it's the orbital that the electron in the hydrogen atom occupies. That volume of space, that energy level. And actually, this is not a good, let me go to the next slide. There, this is better. So the distance from the nucleus in probability terms says that you're more likely to find an electron in this region from the nucleus for a hydrogen atom in that 1s orbital, right? It's not going to be at the nucleus. Right? It just will not be there. The amount of energy required to put it there is just too much. So most of the probability says it's in here, but it could be found out here. Small probability. Okay. So what are we getting at? Schrodinger's equations, those wave functions, lead us to another theory, not the Bohr model, but now we're getting into quantum mechanics. Quantum derives from that earlier description as electrons can only move from here to here. It's quantized. Certain amount of energy, a quantum of energy, will get you from here to here, or you give it up when you go from here to here. But in addition to those equations, we have to always keep in the back of our mind that this is merely probability. We don't know exactly where it is. Okay. Now, those equations and future equations that were derived from Schrodinger's methods can be applied to other elements, all the atoms in the periodic table, with some modifications. So those have developed over the years also. And there are variables in those equations, 4 of them, called quantum numbers. And those numbers, when they plug them in the equation, give the probability of finding that particular energy electron in a space. So we're not going to go that far. We're not going to use the mathematical equations. We're just going to learn the quantum numbers, because if we know the quantum numbers, we can describe the electronic structure of an atom. And that's where we're headed. We want to know the structure of the electronic cloud around an atom so that we can understand how the periodic table is structured, because they're joined at the hip. Okay? All right. So these 4 quantum numbers are given letters. Right? We start with the principal quantum number, which is related to Bohr's model. And it can be any whole number, as many as you want, up. Keep going. 1, 2, 3, 4 on up. Then we have the L quantum number. This is the angular momentum. This is the principal quantum number. This is the angular momentum quantum number. Well, this one is related primarily to energy. Based upon Bohrs model, this talks about energy. This one, angular momentum, describes shape and size of the orbital. And it can have anything, and these, think of this as a tree or a root. You get to this one, say you branch off at this root, and that root can go in these many directions, or this one can go in these many directions. So we're subdividing. So for each one of these, we can take, go from 0 up to n-1. Okay. So if we have 3, we can go 0, 1, and 2. Or if we're in this level, 4, L's can be 0, 1, 2, or 3. See what I'm doing? I'll pause for in case you have questions. Okay, questions? Oh, say it again. Okay. If we're at one of these individual energy levels, say we've got an atom here and we're at n=3. And within that level, you can have these sublevels. Okay. And these sublevels, you can have as many sublevels here as n=3. You could only have 2 here. Let's see. 1, 2, 3, 1, 2. You can only have 1 there. Okay. And these individuals can be 0, 1, and 2 for that level. These can be 0 and 1. That can only be 0 for the L number. Okay. All right. So within each one of these, M sub L, or the magnetic quantum number, that implies direction. And you can take any one of these, 0, 1, 2, 3, 4, 5, whatever it happens to be, and you can subdivide that one into -L, and we're going again in whole number increments. We're going -L up to 0, and then beyond that to +L. So if this happened to be a 2, right, within this level, then you can have M sub L's of -2, -1, 0, +1, +2. So we're branching. We're taking these sublevels that came out of these principal levels, principals to L's, now to M sub L's, and each one of these. So the 1 could be what? -1, 0, +1. 0 can only have 0. That's it. Okay, and then one last. This is the spin quantum number. And it can either have +1 or -1/2. So +1/2, -1/2. Think of these as electrons going into these various levels. So if we're at level 2 here, and let's just say that came from a 3. Start with a 3, then we go to a 2, here. We're at 3, 2, then the sublevel. Which sublevel do we want? Let's just say we're going to +1 sublevel. Within that sublevel, you can have a +1/2 or a minus. Now we're at the level where, for argument's sake, for ease of understanding, there's an electron right there. There's an electron right there, possibly. Or if we go to this one, you could have an electron, 2 electrons there, or 2 here, 2 here, or 2 here. Okay? Now let's use what we learned. There's a slide on all this, but I thought it'd be better to draw it out. All right, that came straight out of your book for the good of the video. Actually, this slide illustrates one useful it's useful interpretation. So if we're going to write the electronic structure of an atom, we're going to start from the low energy end and start writing these orbitals so that we can put electrons into them. And when we do that, we can't afford to have all these jumble of numbers. So we gave the second level letters. So if it's at this level, if it's an L0, we call it S. And if it's an L1, we call it P. If it's a 2, we call it a D. If it's a 3, we call it an F. Now you can go beyond that. But for ground state atoms, that's as far as you need to go. Because we don't have any more atoms at ground state with anything above F. But if you promote an electron to a higher energy level, you might go to a G or whatever else is out there. But that's why this one is 1s. So at this level here, it has only 1. Remember, the number of these that you can have is equal to that number. So you start at 0, you're done for that level. If you have 2, then you can start at 0 and have 0, 1. So 2 can have an S and a P. And a 3 can have an S, a P, and a D. And a 4 can have an S, P, D, or an F in its sublevel structure. That's what they're showing here. S, P, D, F, and 4. Principal quantum number, angular momentum quantum number. And then below that, we need examples to make sense of below that. Okay. All right. So, 1:30. How much time have I wasted on it? We have 15 minutes. Okay. I'm not going to make it. All right. Let's see what we can say about this. For principal quantum level n equals 3, determine the number of allowed subshells, that is, those with L numbers. Right? So if we have n equals 3, what can we have at L? We have 0, 1, 2. 1, 2, 3, 3. We can have 3. They could be 3s, 3p, 3d. Okay. For L equals 2. So let's say we don't care about this one right now. We're just going to say L equals 2. L equals 2, which is what? That's SPD. This is given the letter D. Determine the magnetic quantum numbers for this one. So remember, the magnetic quantum numbers are -2, -1, 0, +1, +2. So once you have this level, you can subdivide it into 5 individual levels, magnetic levels. Sometimes they call them orbitals. So you have 5 at the D level. Now, before we get too far, I've got slides on this, but stream of consciousness. When you look at the periodic table, the highest energy levels that are being filled with electrons. For these two, we have L equals 0, S orbitals. They're being filled. For these, you're filling P orbitals. So you can have 6 electrons. Right? For P, let's do that. P would be L equals 1, right? So you can have -1, let's see, yeah, -1, 0, +1. Okay, what's below this one? Well, this is M sub L. So what's below that one? Your M sub S's, right? So you can have a +1/2, -1/2 on a cross. 1 electron each. 1, 2, 3, 4, 5, 6 at that level. 1, 2, 3, 4, 5, 6. This level, you got S's. 0. 1, 2. +1/2, -1. At this one, you're filling D orbitals, which is what? 5 levels with 2 electrons each. 10. 5, 6, 7, 8, 9, 10. And these are all F's. So F is a 3, -3, -2, -1, 0, +1, +2, +3. 7 orbitals with 2 electrons each. Should be 14 of them, right? That's how the table is structured. Okay. These are representations of what the orbital should look like. S orbitals are spherical. Okay. Now, from the outside, they look like solid spheres, but on the inside, depending on what level you're at, one S orbital has just a simple distribution. 2s orbital has a node, right? So you have right there, you have no probability of finding electrons. Whereas the 3s orbital has 2 nodes. Okay? They're still spherical. P orbitals, L equals 1. They look like dumbbells. Right? So they're oriented on the axes, X, Y, and Z. And that's why the M sub L, or the magnetic quantum number, indicates direction. And for that direction, one direction will be on the x-axis, the other will be on the z-axis, y-axis, and the other on the z-axis. For the d orbitals, they get a little bit more complicated. Right? You got 5 of those possible. Right? And their shapes are kind of cloverleaf dumbbells, except for this one that has a donut in it. Now, remember, these are all mathematical descriptions. Right? These are representations of the math. These have not been observed, but they do explain the evidence. And then D is even wilder than that. Okay, you don't need to know this stuff. S and P's, if you understand those pretty well, then you'll be in good shape. Right, so we've got some rules. The Pauli exclusion principle simply says that in any given atom, no 2 electrons can have the same set of 4 quantum numbers. So they can have the same N, L, M sub L, and if that's the case, then the last one, M sub S, the spin number has to be different. So when you have 2 electrons with those same 3 preceding numbers, then the last 2 have to be different, +1/2, -1. Every electron gets its unique set of quantum numbers. That's all that says. Now, it gets kind of complicated the more electrons you try to shove into an atom. And that modifies the energy levels. And the wave functions that have been developed for each atom take that into consideration. In other words, you've got more electrons, then it modifies the way that the energy levels and the probability distributions are described. They generally prefer that as you add electrons in protons, you're building your atoms, get bigger and bigger and bigger, the electrons go into the lowest possible energy level. So we build them from the bottom up. And let's see. Well, I thought we were going to get that. We will eventually. So what we normally see is that for this orbital structure, the principal quantum number roughly describes the energy level, but there are variations within that energy level. Right? So the P's are slightly higher than the S's and the D's are slightly higher than the P's in the energy. But when we start cramming more electrons in there, you get interactions with the electrons. And those interactions, as you add the electrons, they shift the positions of these, say these D's, especially the D's. So at a certain point, the energy level for the D might be higher than the S, the 4S. 3D may be higher than 4S. Okay? And you see that accounted for in the periodic table. The row numbers, the period numbers, correspond to the energy levels, N's. So if this one is 1, 2, 3, 4, right? 4s, 1 electron, 4s, 2 electrons. But then when you get to here, we've added so many electrons, now they're influencing the position of the d orbitals in the third principal formula. So 3 Ds now are filled here. They're higher energy level than these 4S's. So they come later. But when we get to the P's, 4 P's kick in, they're still lower than, higher than the 3 Ds, higher than the 4S's. So that's one of those flash things that I had to leave in there because it did have this nice picture. But the animation would show you a shift and it would move that 3D above the 4S. Okay, what's the penetration effect? When we draw the electron distributions for these different atoms, remember you had some nodes in there and you had some humps that show probabilities of electron density in those s orbitals. What happens is you get, since you have the probability of finding an electron down here, the 2s has this node in it, but it still has probability distribution down here less than the 2p. So that's why the 2s is still lower energy than the 2p, because this part of the 2s orbital penetrates to a lower energy than the 2p. Okay. You can see that for that particular one. This one would be an S distribution for the 3 principal quantum number. That's 2 nodes here. So these densities are penetrating closer to the nucleus, lower energy, than the major part of the electron density. And if we compare with the 3s, right, there's the 3s right here with a node there, penetration here. So that still gives the 3s less than 3p. And the 3d here is still above these. Even though the major humps are out here, they penetrate far enough so that their overall energy available to the electron is lower than the 3d. Okay, that's all that penetration means. Okay, periodic table. Testing. Okay. Now that we've learned how to, well, we've learned something of the electronic structure of elements. We haven't actually written out the complete electronic structure of an element, but we will. But I want to put that on hold for a second, and let's look at the development of the periodic table. Because they're both, the periodic table and the electronic structure are going to dovetail together. So, the first indication that elements had related properties and that they could be organized in a logical fashion was noticed, was reported first by Johann Doppelreiner. He was German. And he noticed what he called triads. In other words, elements coming in threes that had similar properties. The most obvious is the halogens. Chlorine, bromine, and iodine all exhibited similar chemical behavior. Now, their physical properties were somewhat different because chlorine is a gas, bromine is a liquid, and iodine is a solid. So we couldn't relate them that way. But they did have similar chemical properties. And there were other groups. That was in the late 18th century. Then about a half century later, two chemists recognized even more extensive properties. By this time, more elements had been discovered. So they had more to work with. And both Julius Meyer and Dmitry Mendeleev came up with tables of elements that they thought were arranged in some fashion that could be used to help others understand why they were where they were, and to relate their physical and chemical properties. Well, the difference between the two, Meyer and Mendeleev, is that Mendeleev not only put his elements related by their properties, but he also introduced the concept that was forwarded by Cannizzaro, a student of Avogadro, pardon me, both Italians. Cannizzaro was a teacher, and he wasn't satisfied with the way chemistry was being taught in those days. So he used principles that were proposed by Avogadro. In other words, the relationship of volume of gases to moles. Use that to help him write a complete manual for his chemistry students. That was different than any other that was being used in those days, particularly in Europe. Well, the work that he did there and the work that came out of his publication and introduction at the in the meeting, the chemistry meeting in 1860, 1960 in Karlsruhe, Germany. The work that came out of that was picked up by a number of chemists, but in particular, Mendeleev. Mendeleev saw the value in understanding the relative masses of known numbers of elements. In other words, the mole was starting to take shape. So Mendeleev put his elements in order, and when he came to a place where the next heaviest element was to go, sometimes it didn't match with the properties in its group. And when that happened, he skipped it. He skipped a space there and moved it over into the next group where it did share similar chemical and physical properties to those members of the group. The difference between Mendeleev and Meyer's approach was that Mendeleev not only skipped that spot, but he predicted properties for that element, physical and chemical properties for that element. And he said, one day somebody's going to find an element, it's going to fit right there, and it's going to have these properties. And he was right. Every time he predicted, he was right. They eventually found an element that fit Mendeleev's properties. And that's why Mendeleev gets the lion's share of the credit for developing the periodic table. Okay. So let's see. This is not the best place to start with a periodic table. Let me skip down a couple of slides. I should put these in a different order. Let me go back. Here we go. Overall, the periodic table is divided into metals and nonmetals. Metals occur in most, and the majority of the elements are metals. And there's a diagonal line that runs right down here like this, down there like that. And that's your dividing line between metals and nonmetals. Nonmetals on the right-hand side. Except that there are some elements that are very close to that line, these blue boxes. Those elements, under certain circumstances, exhibit metallic behavior, and under other circumstances, reactions, they act like nonmetals. So they're called metalloids. We also have groups. Now this is the old numbering system. Roman numeral, most of the time it's Roman numeral 1, 2, 3, 4, 5, 6, 7, 8. And there is value in that. And it has to do with the octet rule, which we'll introduce later and talk about a little bit more. But now the groups or the columns are numbered consecutively from left to right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18. 18 columns. And then the periods will have numbers here also. 1, 2, 3, 4, 5, 6, 7. Then there are other major groups. The lanthanides here are a group of elements that fit right in here. And they're named after lanthanum, which is the first member of their series. And then the actinides are just below that. They fit in right here. And of course, they're named after actinium. Now let's go back. Here we go. Other groups have names. The noble gases, obviously. They don't form compounds willingly with any other elements. Some of them can be forced. The halogens are the next ones over, right? Like fluorine, chlorine, bromine, iodine, astatine. And then the first group is alkali metals. Second group is the alkaline earths. or the alkaline earth metals. Everything in here is called transition for obvious reasons. It's transitioning from one side to the other. Now, sometimes you'll hear parts of the periodic table referred to as representative elements. The representatives are these first two groups plus these last six groups. Those are the representative elements. Okay. Let's see, we did that already. Transition. I'm missing something. No, I guess not. Okay. Now, when we're building elements from the lighter ones to the heavier ones, as we go, one proton at a time, one electron along with it at a time, those electrons go in order of increasing energy. Right, so we fill from the bottom up, low energy, and if those positions are occupied, we have to move to the next higher energy level. That's known as the Aufbau principle. Aufbau is a German word. I don't speak German, but I looked it up. And basically what Aufbau means is do it this way. So that's the way we do it. Lowest energy to highest energy, gradually one electron at a time. Here's an example of how we write the electronic configuration of an element, right? Remember the 1s, 2s, 3s, 4s, those are the principal quantum numbers. And then the next ones are the letter equivalents of the angular momentum quantum numbers, the L numbers. So this would be a 0 and this would be a 1. All right, so that's oxygen. Let's see. Let's do another one. Let's do a neighbor of oxygen, say nitrogen. Right? So nitrogen has 7 protons and the neutral atom will have 7 electrons. So we start filling them in. 1s, 2. 2 electrons can go in s because s is 0 and it can only have an m sub l of 1 layer. Right? So if n equals 1 and l equals 0, because it can only have 1, then m sub l will also equal to 0. And then you can have an m sub s of plus 1/2 minus 1/2. So we can only put 2 electrons at this level. When we get to the second one, we can have a 0 and a 1. Okay? And then for this one, we can have s is 0, or we can have the 1 can be minus 1, 0, or plus 1. Okay? So we can have 2 here, and the p can have a maximum of 6 electrons, right? 1 for each level. Plus 1/2, minus 1/2, plus 1/2, minus 1/2, plus 1/2, minus 1/2. 6 here. So a maximum of 6. But that's more than nitrogen needs. It only needs 3 more. So the last 3 go into the next highest level. Okay? That's nitrogen. So here we have Hund's rule. Hund's rule simply says that when you're filling a subshell like this, it can have more than 1 level, like 1, 2, 3. You have these 3 levels. Minus 1, 0, plus 1. Okay? What Hund says is you put 1 electron in each sublevel until you've got all of them with at least 1 electron. Then you can go back and put the second one in with the opposite spin. So this would be like that, like that, like that. And we're done. That's it. That's all it will hold. Okay? with oxygen, oxygen has 4 because it's got 8 protons, 8 electrons. So it's got 4 in the p level. Right? So oxygen would have another one here. Now that it's got 3 in that level, we can put the last one, spin down. Spin up, spin up, spin up, spin down. Okay, that's Hund's rule. And here it is on a slide, like 2, 2, and 4 here with up, 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 and 1 down. Notice I write mine a little shorthand than the boxes and the double-headed arrow. I like the single bar. It's quicker and conveys the same information. Okay, concept of valence electrons. Why do we introduce this concept in the middle of everything we're talking about? Because chemical reactions tend to, in fact, they always occur with the outermost electrons, those in the outermost energy shell. So for oxygen and nitrogen, that outer layer is N equals 2. Okay, all the electrons in that level are called valence electrons. They are available for reactions. So when we have 1s2, 2s2, 2p6, which would be 6, 7, 8, 9, 10. What is that? 10 electrons? Well, that's a noble gas, right? We can't put any more. P's can only hold 6 electrons. These are filled, these are filled, these are filled. When you get to that level, you have a noble gas. And in this case, it's neon. Well, let's suppose we have oxygen again. There we go. The number of valence electrons in oxygen, neutral atom, are these. 6 valence electrons. Okay? All the electrons that have the same principal quantum number, and they're the highest energy of the group. If we had a level 3 out here, we wouldn't count the 2s, just the 3s, just the level 3s. Those are the valence electrons. All right. So I mentioned this earlier in our discussions. Which orbitals are being filled in various places in the periodic table? I mentioned the S's are being filled here. Remember, S's can only have 2 electrons. So you put 1 here, you get those elements. You put 1 here, you get those elements. They're different S orbitals, right? This is a 2s, that's a 3s, 4s, 5s, 6s. Okay, so they're different energy levels, but they're still S orbitals. And we're filling them that way. Then over here, we're filling the p orbitals. Remember, p's can have 3 levels with 2 electrons each, which means 6 electrons. So you have places for 6 elements as you add electrons and protons together to make those new elements. And then for the d orbitals, those are numerically equal to 2, which means -2, -1, 0, +1, +2, 5 subshells or suborbitals, and 2 electrons each means 10. So you have 10 across here. And then F's have the potential for 7 subshells, which means 2 times 7 is 14. So that's the way they're filled. This also has the period numbers. Right. And those period numbers correspond to principal quantum numbers for the S level and the P level. When you get into the transitions and the actinides and the lanthanides, then you change the principal quantum number. So this is not strictly speaking the quantum number for everything in that row. All right. Now, how do we add the electrons so that we get them in the right energy level? Well, there are two ways to do it. One way is to use the periodic table. The other way is to use the diagonal diagram. So notice that when n equals 1, we only have s orbitals. That's it, right? Because L can only be 0. That's all. That's as far as you can go. N equals 2, you can have s's and p's. N equals 3, you can have s, p's, and d's. N equals 4, you can have s, p, d, and f. 5, you can have s, p, d, f, and g. We don't write g, basically because we don't need g. Right? With f and principal quantum number levels, we can get all 118 elements that are currently on the periodic table. So we just write it out to this far, and then we stop on this one at D and this one at P. And the reason we do that is because now we're going to use diagonals. So the diagonal says, okay, we fill that one, then we come back and we fill this one, then we come back and fill that one, and then this one. Then we come back and fill this one and that one. Now, instead of going to 4P, we can go back up to 3D, fill that one, then to 4P, then to 5S. Then we go back to 4D, and to 5P, and to 6S. Okay? That diagonal approach will give you the electronic configurations for most of the elements. There are some minor exceptions. Okay, so let's write out the electronic configuration for these examples. How about sulfur? First of all, how many protons and how many electrons does it have? It has 16. Okay, so we start and we write from left to right, increasing energy. 1s, 2s, 2p, 3s, 3p, and if we need any more, we'll go. So, let's start using up our electrons. Low energy to high energy. 2 here, 2 there. So that's 4. 6 here. That's 10. We got room for 6 more. 2, 4. Okay, let's count them up. 2, 4, 6 is 10, plus 6 is 16. So that's the electronic configuration for sulfur. Let's see if we got, do I have a periodic table I can use? Well, I'm not a good one. Okay. Right, there's also an abbreviated way to write this. Notice that we have, these are our valence electrons. And the valence electrons occur once you've reached the neon gas phase. Once you've reached neon gas, this one would be neon. Right? That would be the electronic configuration for neon. It's noted, notice it's noted as the core. And these are the valence. Right? You can write it that way. How about barium? I need a periodic table that I can show up here. Let's see. All right. Notice with sulfur, I'm going to come close to the camera for this one. Notice with, here we go, sulfur. Sulfur's right here. What have we filled? Well, the first period, we filled the S's, 1s2. Then we filled the 2s, 2s2. Then we went over here, 2p. 1, 2, 3, 4, 5, 6. We filled all the p's. Then we went back over and started on the 3s. 3s1, 3s2, okay. Then we went over to 3p. 3p1, 3p2, 3p3, 3p4. Okay. If we know that in advance, then we can say, and we know which ones to fill. And we can write the electronic configuration from the periodic table. Then if we use our shorthand, we can go up here to neon and say, okay, neon is our core. Then we say, okay, beyond neon, we come back here to 3s2, and then over here to 3p4. That gives us sulfur without using the diagonals. How about barium? Where's barium? Barium is way, way down here. There. Let's see. I can see it better over here. Barium has 56 electrons that we have to place. Right? We could do the same thing as before, except, in fact, maybe we should do it complete. Let's see. There's sulfur. All right, barium, we're going to use the shorthand version. All right, so barium would be, we go backwards. There's barium, go backwards, and now we have to go up to xenon. So xenon has 54. So xenon takes 54 electrons, and then we get into the valence electrons for barium, which would be 6s2. That's why it's there. That's why it fills at that position. If we were to write this whole thing out, it would take a couple of lines. Let me do one. How about iron? Iron is 26 electrons. Right. This one is xenon, 54, and then 6s2. Let me do iron. Europium is even worse. So let's just do iron. What did I say? 23? No, 26. 26 electrons. Yeah, that's a good one. Okay. We want to write this using our periodic table. Okay. If we start writing this out, 1s, 2s, 2p, 3s, 3p, 4s. Now what happens when we get to 4s? Our periodic table again. Where's 4s? 4s is right over here, potassium. 4s1, 4s2. Then we get to 3d. Right? You have to back up one when you get into the, if you use the diagonal, it's obvious. But if you use your periodic table, you have to know that once you get past 4s, you're in the 3ds. So 3d, 1, 2, 3, 4, 5, 6. 3d6 is beyond 4s. So let's fill in the rest of them. 2, 2, 6, 2, 6, 2. Now, do we have the right number? Well, let's see. 2 plus 2 plus 6 is 10. 2 plus 2 plus 6 is 10. 26. That one's done. Shorthand would be, we look at iron. Let's see. Look at iron and go backwards. Okay, now we got to go up to this period and down to the end to argon. So we take argon. Argon is let's see. Argon is 18. So that leaves us 8 more electrons. So argon is going to be down to 3p6. And then we have 4s2, 3d6. Let's see, is that right? Yes. Okay. Okay. So europium is a little more complicated. In fact, where is europium? Europium is a lanthanide. You're filling F orbitals for europium. So we're not going to deal with that one. That's a little too much. But this is the the abbreviated electronic configuration. All right, let's move on. Let's talk about trends. Trends in the periodic table. What do we mean by that? Well, there's certain, in this case, quantitative values that can be assigned to each of the elements. And we want to know in what direction do they increase and decrease. Because they do that. We're going to focus on ionization energy, electron affinity, and atomic radius. So we need to define what those things are. Right. Ionization energy. Ionization energy always has to be written this way. There's your symbol. And that element must be a gas. And what we're going to do is we're going to add energy, and that's what that delta means, add energy. And we're going to kick off one electron and leave us an ionized gas. And here's the electron that's released. Okay. How much energy does it take to make that ion? This is known as the first ionization energy. Because that's the ground state, and we're kicking off one electron. So much energy is required per mole. You can also do second ionization energy. You take this gas, add some more energy. Now you get a 2+ and another electron. Okay. And you can keep doing that. So the trend here in this case is that each time you kick off another electron, you have to add more energy per mole than you did for the first one. And that's logical, because here we're trying to remove an electron from a neutral body. Here we're trying to move an electron from an ion. So the positive ion is attracting that electron with more force. It takes more energy to get it off. All right. Notice also that you have to be in the gaseous phase. If you started from solid or liquid, say that you're using a metal. The metal typically is a solid at room temperature and pressure. Right? What are you going to have to do to get that electron off? Well, if you're just adding pure energy, like you're heating it, then you've got to go through the liquid phase and the gas phase before you can remove that electron. That has no useful information about the energy required to remove an electron. So you have to start in the gas phase. Okay. Now, of course, I know what you're thinking. You can get rid of an electron if you have a metal and you shine light of the right frequency on it, you can kick off an electron. Okay, that's true. But we're not talking about that for this situation. Ionization energy is more of a bulk process. Notice also here for magnesium, it takes 735 kilojoules per mole for the first ionization energy. Then it takes about double that for the second ionization energy. Now, when you get down to the third electron, look at it jump, right? About 6 times as much energy, whereas it doubled the first time, now it's 6 times. Why is that? Notice where magnesium is located in the periodic table. Right here. Valence electrons, it has 2. Right? Those electrons are ready to leave. So it takes a little bit of energy for the first one, a little more for the second one. When you get down to the third one, you're not in the valence electrons anymore. You're in the core. And core electrons are held very tightly. So that's the reason for the jump. And you'll see that for any element. Valence electrons come off with increasing amounts of energy in a fairly orderly sequence. But once you get into the core of any element, the amount of energy required jumps way up. Okay. Now, how about the trends in the periodic table? When you look at the periodic table, in terms of left to right, along a period, as you go left to right, the ionization energy, the first ionization energy increases. Right? The electrons are at basically the same energy level, but what's happening? You're adding protons. So you're adding more protons to the core, and that increases the effective nuclear charge, which holds the electrons more strongly. So as you go from left to right in the periodic table, you increase the ionization energy, the first ionization energy. How about up and down a group? Well, as you go down a group, the electrons are being added into higher and higher orbitals. So they're farther from the nucleus, which decreases the nuclear influence. Plus, even though you're adding more protons in the nucleus, there are electrons between the outer shell and inners. And those inner ones are shielding the outer electrons from that positive charge. So as you go down in a group, the first ionization energy decreases. So if you go back the other direction, from bottom to top, you are increasing the first ionization energy. Now, put that all together. First ionization energy from lower left to upper right increases as a general rule. Now, note these are trends. These are not absolute. And you will see variations in that trending. Okay. Here's an example of first ionization energies for all the elements on one chart. And you'll notice that as we go, here's hydrogen's first ionization energy. Right? It really wants to give up that electron. But helium, what's the difference between hydrogen and helium? The helium atom has a complete 1s orbital. It's essentially the core. So core electrons require much more energy to remove. In fact, the difference here is about what? Right, 1250 and 2500. It's about double the energy. And then you come back down to lithium. Lithium, you're removing, the first electron you're removing is a valence electron. It's only one of them, right? So it takes a little bit of energy. But you move to the right to beryllium, and it takes a little more energy to remove that first electron. But notice when you get to boron, boron is here. You've gone from, let's see, let's get a better picture here. You've gone from lithium to beryllium, and now over here to boron. It takes less energy to remove that electron than it does for beryllium. Why is that? Which electron is being removed? that first electron in boron is in the p orbital, right? 2s2, 2p1. The p orbitals are slightly higher in energy, so it takes less energy to reach infinity. That's why boron takes less energy than beryllium to remove that first electron. But then carbon jumps back up, nitrogen jumps back up, and then oxygen dips back down. So why is that? Remember, nitrogen nitrogen has 7 electrons, oxygen has 8. So if we write their structures, electronic configurations, this one has 3 here. S2, 2s2, 2p, 4. That gives you 8. Okay, what's the difference? The difference is in the p orbitals. This one has 3 sublevels. So does this one. This one has 3 here. 1 there, 1 there, 1 there. This one has 4. Okay, so which electron is being removed? For this one of these is being removed. Takes a certain amount of energy. For this one, that one's going to be removed. And notice that it's sharing a subshell with another electron, which means there's repulsion there. So that little extra repulsion makes this one easier to remove, less energy. So that's why we came up to nitrogen and then we get back down to oxygen. Now, when we go to neon, fluorine has added another proton in addition to that electron. Right? So fluorine is going to be like this. Right? And now, with that extra proton, you're increasing the effective nuclear charge beyond the advantage of this repulsive force. So now fluorine is back in the trend, and we're back up to neon. Noble gas is nothing but core electrons. And it takes a lot of energy. Right? You see those switchbacks periodically. Here's one, there's one. Right? What are all these right in here? Those are transition metals. Okay, so they jump up and down. Right? You get some trends in there and you get them jumping up and down. And we could spend time talking about that, but to be frank, there's not that much time to finish this chapter. Okay. Oops. There. We talked about the exceptions, and they're basically due. Major factor is electron repulsion. At least for the p orbital example. But for the beryllium to boron, it's more energy level because you're removing electron from boron in the p level versus the s level for beryllium. Well, yes, that's true. I just had to think for a second. Okay, let's see if we can use what we know about the trends of ionization energy. Which one of these requires more energy to remove an electron? Remember, in a period, the higher energy required for removal is to the right. Sodium is way over on the left, chlorine is way over on the right in the same period. So that means chlorine takes more energy to remove its first electron. How about lithium and cesium? The relationship there is in a group. Cesium is way at the bottom, lithium's at the top. So the trend there is the bottom one takes less energy to remove its electron. So lithium would require more energy. How about second ionization energy for lithium versus beryllium? Okay, For this one, we need to see, all right, who's got valence electrons? So lithium and beryllium. All right, let's see, here's lithium. You take one electron out of lithium, you're in the core. For beryllium, you've got 2 electrons that you can remove before you get into the core. So lithium's second ionization energy is going to be much, much higher than beryllium's. All right? Here's an example, right? Just follow along, increasing atomic number, sodium, magnesium, aluminum, silicon, just keep going on up. And what you find is that here's the trend. There's the second ionization energy. It takes the third for magnesium. You're getting into the core here. And you have to remove more electrons before you get into the core as you increase the number of valence electrons. That's the purpose of this illustration. Okay, electron affinity. So what does electron affinity mean? It's tempting to say electron affinity is just the converse of ionization energy, but it's not. The converse of ionization energy would be electrons coming back to the ion. But here we're looking at the affinity of an electron for a neutral atom in the gas phase. You still start with the gas phase, and then an electron is added, and you end up with a negative electron. Okay, so what happens when an electron arrives and is captured by a neutral atom? When the electron is at infinity, away from the atom, it has maximum energy. So when it is captured by the atom, it loses some of that energy. It becomes more stable, lower energy level. So it has to give off energy. It's an exothermic process. Okay? So that means the value of this is going to be negative. Right? Exothermic means negative. A negative value of kilojoules per mole, usually. Okay, so the more strongly an electron is attracted to this atom, the more negative that number will be. Okay, so when we say the electron affinity increases, we mean the number gets more negative. Okay, keep that in the back of your head. The more negative the number, the stronger the attraction. Okay, now that being said, when we go from left to right, the electron affinities are strengthened, which means a more negative number. So from left to right, we get more negative. If we go down the group, they get more positive. That is, the electron affinity decreases as you go down, and then the value itself gets more positive. So coming back up a group, you get more negative. And going from left to right, you get more negative. So from lower left to upper right, you increase the affinity of the electron for the atom, and the value becomes more negative. Okay? How about atomic radius? That's the last one that we're going to discuss here. By the way, what do we mean by atomic radius? How do you know? Right? What do you have to know for an atomic radius? You got to know the boundaries. Right? When do you reach the outer layer of an atom? Right? It's sort of a guess, right? Because we talked about earlier that we really don't know where those electrons are, right? Based on Heisenberg's principle, we know more about their energy than we do their position. So this is sort of a guessing game. And it depends on whether the atom is naturally in a gaseous state or a liquid state or a solid state as to what those differences are. But in general, if you can identify the distance between two nuclei of atoms that are in close proximity, say if they're in a crystal structure of a solid, or if they're in a diatomic molecule like O2, if you can identify the distance between the nuclei, then you just take half of that. And that is considered the nuclear radius. Half of this value would be here, like that. Okay? So there are a number of ways, but basically two that are recognized, two types of atomic radius determinations. One has to do with the metallic radius. So if you have metals, and they're solid, of course, well, except for one, mercury, then they're usually fixed in a solid matrix, with that one exception. And if that's the case, then you can investigate the internal structure of that solid with X-rays. We use what's known as Bragg's equation. And it's a little more than we can do here. Stick around for next semester and we'll talk about it in detail. But what it does is it tells you what's the distance between adjacent layers of atoms. And that will also tell you the distance between the nuclei. And that gives you an indication of the metallic radius of the atom. The other type is covalent radius, where you have two or more atoms bound together with that shared bond, shared electron bond. And there are different ways to measure that distance between those nuclei. And we try to use homonuclear diatomics. That is, the same atom, pairs of the same atom. Depending on the element and the equipment you have and various other factors, you can use X-rays, you can use electron bombardment, you can use neutron bombardment. Sometimes you can even use microwaves or a combination of them to give you information. And sometimes you want to use more than one method and compare the results. They won't always be the same. In fact, they're never the same. So sometimes you do several different techniques and you average the values. Okay, so what's the trend for atomic radius? Well, the radius of the atom, from left to right, the radius decreases because you're increasing the number of protons in the same energy level. Then the added electrons are feeling a stronger pull, and that tends to shrink the size of the atom. So the atomic radius from left to right decreases. As you go down a group, you're adding electrons to higher and higher energy levels, which expands the size of the atom. Right? Not only is it higher energy levels, but they're further from the nucleus. So when you do that, you're ballooning the atom with electrons. So from top to bottom in a group, you get an increase in atomic radius. Or if you go the other direction, from bottom to top, you decrease the atomic radius. Okay. So as a trend, overall, from lower left to upper right, you decrease the atomic radius. Okay, and this is an illustration. Right? These are only representative elements, right? The S group and the P group. When you get into the transition elements, then it kind of bounces up and down. So for trending purposes, this is a better illustration, just using the representative elements only. Okay, which should be the larger atom, sodium or chlorine? Well, they're in the same period. Sodium's on the right, chlorine's way on, sodium's on the left, chlorine's way on the right. So chlorine should be the smaller and sodium would be larger. How about lithium and cesium? Again, they're in the same group. So as we go down, we should see cesium as the larger atom. Okay? Now, let's look at, instead of trends for the whole atom, let's look at the individual orbitals. Okay? So if we're looking at 1s only, and we're comparing hydrogen and lithium, right? Lithium has 3 protons and 3 electrons. Hydrogen has 1 proton and 1 electron. Then what about that 1s orbital? Which is larger? Well, which one has the greater effective nuclear charge? Lithium, with 3 protons. So it's going to shrink that 1s orbital, right? We're not talking about anything out there beyond, just the 1s orbital. So lithium should have the smaller 1s orbital. Hydrogen will have the larger 1s orbital. Which one is lower in energy? The one that's lower in energy is the one that's smaller in size, because the electrons are closer to the nucleus, and closer means lower energy. So that means lithium, 1s orbital, has the lower energy. So if you have acquired that assumption that a 1s is a 1s is a 1s, set that thought aside. Relatively speaking, within the same atom, then the 1s is a lower energy than the 2s. But if you compare different atoms, then the 1s for one could be radically different in energy level than the 1s from another one. Okay. So let's arrange these in order of increasing ionization energy. Right, let's see, where are they located? Oxygen, fluorine, sulfur. All right, here we go. Let's see, oxygen's here, fluorine's there, sulfur is here. So the trend is lower left to upper right. That means sulfur should be a lower ionization, lower ionization energy than oxygen, which is lower than fluorine. So sulfur, oxygen, fluorine should be the order of increasing ionization energy. How about atomic size? Atomic size is just the opposite. So it ought to be fluorine, oxygen, sulfur, right? Increasing size. Okay, these are some final thoughts. There's nothing spectacular there. It's just pulling everything together. This is important. The number and type of valence electrons determine the atom's chemistry. That's true. You can determine the electronic configuration from the organization of the periodic table. That's true. Certain groups have special names. Yeah, that's true. Basic division of the elements in the periodic, metals and nonmetals. That's the gross division, metals and nonmetals. So those are the only trends that I've, the only final thoughts about atomic structure and the periodic table.